Hello, everybody. Thanks to be here today. I will present you part of my thesis results. So for the next 10 minutes, I will talk about very fancy animals, bivalves, and their biodiversity through times. If my slide could change, it will be great. Yeah. So first, to introduce my work, I have to present something you little heard about, global warming and climate change. Global mean temperatures are now approaching the upper bound of what has been observed over the past 2 million years and become quickly key issues in recent decades. The gradual loss of habitats and the overstepping of tolerated temperatures is leading to an overall decline in biodiversity. But I thought the current global warming is faster than any previous warming. Even in deep time, we're okay with that. Earth has experienced even greater variation in temperature. For this reason, the large-scale study of diversity dynamics make it possible to understand past responses to climate change and to incorporate these insights into current predictive models. This is what Machiavelli means in this quote that I like so much. The global diversity of a group is clearly dependent of biotic, abiotic, and ecological change through time. This is what is studied much of the time when we focus on paleobiodiversity. We are searching for causes of the diversity. A large amount of studies tend to depict a comprehensive taxonomic richness of invertebrates, like Bangback and the ecospace, or Sepkoski and the marine assemblages. But less attention had been paid on the evolutionary faunas and ecological history of bivalves, even if they are very, very great models. They have a large range of traits and ecological adaptation that allow us to be distributed all around the world, and their abundances and good preservation in the fossil record greatly facilitate the study of their taxonomic evolution through the Phanerozoic. So my work is to question the effect of climate change on the diversity and the ecology of bivalves. In attempt to do this, I use a database published by Payne and M in 2020, but it's a general marine database downloaded from the paleobiodiversity database. So I had to extract only the data of bivalves, which represent above 77,000 of occurrences. In addition, I put for each family or ecospace based on the work of Mondale and Harris, also published. So I make the diversity analysis, and in order to do this, I use two different methods. The first one is a range through diversity, and probably the one you heard about, where we count each taxon in each stage. And the second one is a more statistical approach called shareholder quorum subsampling, SQS. In general, this method shows reduced curves, but keep the same global trajectory than the more classical method as range through diversity. When finally I have my results, I made a factorial analysis in order to polarize the family that share the same dynamics over time. And this is what we call evolutionary faunas. During the process, a family receives a score reflecting its importance in a factor, and each factor is a proportion of the total diversity curve. And so this is a result of the global diversity of bivalves. And what we observe is a general increase through the entire Phanerozoic, but remind you just what I said just before, some family could have more particular trends within this global augmentation of the taxonomic richness. And yes, bivalves have four major faunas. The first one starts during the Ordovician with a maximum of richness reached during the Silurian and declined through the Devonian to the middle of the Permian. The second one succeeded to the Ordovician Devonian fauna during the upper Devonian, but the final Paleozoic fauna appeared earlier, just after the in-ocean crisis during the Silurian. And if the first fauna's turnover is quite progressive, as you can see, The shifts between the second and the third fauna is abrupt and mainly driven by the Permo-Triassic crisis. The mid-Mesozoic fauna appeared during the Carboniferous and declined through the Upper Jurassic. This is concomitant with the acceleration of the diversification of the last fauna, the modern one. And if we look closer in each ecological traits of the faunas, we obtain this. First, we have a majority of infaunal forms, mainly suspensivores and depositivores. Some of the bivalves are slowly motile, but in majority, they are basally attached to the substrate. But we can observe a change between the first and the second fauna with the appearance of more deep infaunal forms and carnivorous bivalves. Then the mid-Mesozoic fauna is marked by the rise of cemented forms after the Permo-Triassic crisis. The cemented forms are useful for the residual formation during this period, for example, the redists. Why we have this change? It's because there is a collapse in the brachiopod diversity in the same time. This change is also accompanied by an increase of osmotile bivalves like pectens. The modern fauna kept the previous ecological occupation, but with more of other feeding strategy, like parasitism or symbiosis, and an augmentation of recliners and diminution of osmotiles and cemented forms. But what drives those changes? This is a big question. First, we ensure that major biological crises have a little impact on the bivalve diversity, with an exception for the Permo-Triassic crisis, as I presented before. So what we can observe is two distinct progressive changes. The first one is during the Paleozoic, and the second one during the Mesozoic and the Cenozoic. Those two blocks are very similar to the fragmentation of the continents. The Pangea assembly reduced the fragmentation and so the coastline disponibility, whereas the Pangea breakup increased the length of coastal habitats. And obviously, because it's all about a bottom-up cascade, the fragmentation induces change in sea level, but also in continental flux, which are nutrients. So firstly, we have a reduction of continental inputs, and after the Pangea breakup, the nutrients are more available in the water chemistry, sorry. And I don't talk about nutrients availability without something specific in my mind. Nutrients are fuel for the planktonic component, and the planktonic component is the food of bivalves. So what I illustrate here is that the first fauna is very, very, very similar to the Acritox diversity. We don't really understand what happened during the second part of the Paleozoic for the phytoplankton, but there is a change for sure. And this phenomenon is called phytoplankton blackout. The mid-Mesozoic fauna experienced an increase of the calcareous plankton and the origination of dinoflagellate. This is a mid-Mesozoic revolution. Of course, this change will also modify the water chemistry, and we suppose that is one of the factors that could influence the change between the third and last fauna. But ecological changes also happened on land, and it's really interesting when we look at the evolutionary floras. The four evolutionary floras are very concomitant with our four bivalves faunas. The modification on land with the terrestrialization, the first forests during the Carboniferous, the gymnosperm reign, and the rise of angiosperms have probably changed hair parameter, the fragmentation, and so on. But the temporality are very similar, and so possibly driven by more or less the same factors. To put in a nutshell, bivalves have four evolutionary faunas with specific variation on their ecospace. So their feeding, their tearing, their mobility habits. The causes identified that could drive the four dynamics are from abiotic and biotic changes, but also we point that some big ecological change happened in the same time period that implies common drivers. The only shared parameters are linked more or less with the global climate change. So we can conclude that biodiversity is sensitive to climate. Thank you.